Solar wind. The solar wind is the continuous outflow of charged particles that streams from the sun's outer atmosphere into space. The atmosphere is so hot that the sun's gravity cannot hold onto its outer material, and a steady flow of electrons and protons escapes in all directions at speeds of hundreds of kilometers per second. This wind fills the entire solar system and carries the sun's magnetic field with it. When it strikes Earth's magnetic field, it produces auroras near the poles. The boundary where the solar wind finally slows and merges with interstellar space, far beyond the outermost planets, is called the heliopause, and it marks the true outer edge of the sun's influence. Corona. The corona is the outermost layer of the sun's atmosphere, extending millions of kilometers into space. Its defining mystery is its temperature. While the visible surface sits at around 5,500 degrees, the corona reaches 1 to 3 million degrees, hundreds of times hotter than the surface beneath it. How a cooler surface heats an atmosphere to such extremes remains one of the central unsolved problems in solar physics. The leading explanations involve magnetic waves and countless small magnetic reconnection events. The corona is normally hidden by the brilliance of the surface and becomes visible as a pearly white halo during a total eclipse. Transition region. The transition region is a thin, irregular layer between the corona above and the chromosphere below. Across a span of only a few hundred kilometers, the temperature leaps from around 20,000 degrees to hundreds of thousands of degrees. This dramatic jump is one of the least understood features of the sun. The energy required to heat this layer so abruptly does not come from below in any obvious way, since heat should not flow from the cooler surface into the hotter atmosphere above it. The region radiates mostly in ultraviolet light, invisible from the ground, and is studied primarily by space-based telescopes. Chromosphere. The chromosphere is a layer of the solar atmosphere several thousand kilometers thick, sitting just below the transition region. It is normally invisible, drowned out by the glare of the surface below, and becomes briefly visible as a reddish rim during a total solar eclipse. The red color comes from hydrogen emission. Something strange happens here. Instead of continuing to cool with distance from the core, the temperature begins to rise again, climbing from around 4,000 degrees at its base to around 20,000 degrees at its top. Jets of plasma called spicules constantly shoot upward through it, carrying material tens of thousands of kilometers high before falling back. Photosphere. The photosphere is the visible surface of the sun, the layer from which nearly all its light escapes into space. It is not solid. It is simply the depth at which the plasma becomes transparent enough for photons to travel freely, ending the endless scattering of the interior. It is only a few hundred kilometers thick, thin compared to the body of the sun, and has a temperature of around 5,500 degrees Celsius. This is where sunspots appear, cooler and darker regions where intense magnetic fields suppress the flow of heat from below. The granular pattern of convection cells is visible across its entire face. Convective zone. The convective zone is the outermost interior layer, sitting just beneath the visible surface. Here, the plasma is cool enough and opaque enough that radiation can no longer carry energy efficiently, so the sun switches to a different method. Hot plasma rises in enormous columns, releases its heat near the surface, then sinks back down to be reheated, in the same way water churns in a boiling pot. These circulating cells transport energy outward in days, rather than the millennia it took to cross the layer beneath. The rising and falling columns give the visible surface its mottled, granular texture. Tachocline. The tachocline is a thin transition layer between the convective zone above and the radiative zone below. It is narrow, but it may be the single most important layer for understanding the sun's behavior. Below it, the sun rotates as a solid body, all at the same rate. Above it, the sun rotates at different speeds, depending on latitude, faster at the equator than at the poles. This sharp change in rotational speed across a thin boundary is thought to act as a dynamo, stretching and twisting magnetic field lines. The sun's magnetic field, its sunspots, and its violent surface eruptions are all believed to originate in the shearing action of this layer. Radiative Zone. The radiative zone sits between the Tachocline and the core, filling the region from about a quarter to 70% of the Sun's radius. Energy produced in the core moves through this region as electromagnetic radiation, but it does not travel in a straight line. The plasma here is so dense that a photon can travel only a tiny distance before being absorbed and re-emitted in a random direction by another particle. Through this endless scattering, a single packet of energy can take tens of thousands of years to cross the radiative zone. The light reaching Earth today began its outward journey from the core long before human civilization existed. Core. The core is the innermost region of the Sun, extending from the center to about a quarter of the way to the surface. It holds only 2% of the Sun's volume, but roughly a third of its mass, compressed to a density around 150 times that of water. Temperatures reach 15 million degrees Celsius. This is the only place in the Sun where nuclear fusion occurs, because it is the only region where pressure and temperature are high enough to force hydrogen nuclei together into helium. Every joule of energy the Sun radiates originates here. The process converts 4 million tons of mass into pure energy every second. Thanks for watching. The corona is hundreds of times hotter than the surface below it, and nobody fully knows why. If you have a theory, leave it in the comments. Also, please remember to like and subscribe if you enjoyed this video.